Hi, in this video I'll demonstrate how to do the sound investigation 1. So as you can see, when you click on the sound investigation 1 task in manage back, it shows the research question. The research question is measure the time period and frequency of sound waves of different frequencies by measuring the time taken for a given number of compressions or rarefactions. And how does the time period vary with frequency of sound wave? So the main question we want to understand is how does time period vary with frequency of sound wave? So here the independent variable would be the frequency of sound wave and the dependent variable would be the time period. So we will vary the frequency, and for each different value of frequency we would measure the time period. Okay. So to do this experiment on the computer itself, we will use this simulation from Phet. So just click on this, and I'm assuming you know how to install the Java etc. to make this Phet simulation work in your computer. And I've also uploaded Ritwik's project report as a sample. Once you finish the experiment and process all the data, graphs, everything, you have to submit it in the form of a report in a Word document. For that you can use this file as a reference. So your observation tables have been created in this spreadsheet. So download this file onto your computer. So let's start with the spreadsheet. So this is a spreadsheet which you are supposed to download. So it once again explains the aim of the experiment, and your first task is to fill this raw data table. So let me demonstrate how to do that. So I have already keyed in some theoretical frequencies. You are expected to change these initial theoretical frequencies. Just pick a frequency close to this, but it should be different from what I have mentioned here. So I want each and every student to use different values of frequencies. So this is the simulation in Phet. So go to the measure tab and move the stop clock towards the side and put the scale somewhere here. Make the amplitude maximum, and the first frequency, let us take some value close, let us take some value, say 152. Move the frequency slider to adjust it. Okay. So now we need to first note down the time taken for 10 compressions to cross a given point. So the black rings represent the compressions and the white rings represent the rarefactions. So the darker it is, it means the amplitude of the sound wave is larger. Similarly, the brighter the white rings, the amplitude of the sound wave is larger. And the darker it is, it's a compression and it's a high density region and high pressure region, and the white rings represent rarefaction and low density and low pressure regions. Okay, so we'll just pause the simulation first, and let us keep the position, the scale, such that the exact center of one of the black rings coincides with the leading edge of the scale, the left edge of the scale. So now this ring we will call as the 0th ring. So when this is the next ring, so when this ring reaches here, we would count it as one compression has crossed the reference point. So we have to count 10 such compressions. So let's start the clock after making sure it is already at 0. So now when I play the simulation, I can start watching the waves move. So now I'll click on play. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Pause it, and then when it is So now it's very close to being the 10th wave, 10th compression. So now we will go step by step so that we don't miss it. Like this. Yeah. So now 10. So the time is 0.0666. So that's what I have already noted here. 0.0666. You just type it in. So like that, repeat the process and count, note down the time for 20 compressions, 30 compressions. Then change the frequency slider to 313 or any other frequency, whatever you want, and note down the timings. So that's how you complete the raw data table. Next, we need to process this data to get some meaningful information out of it. So for that we will use the processed data table. So in this table we will first measure the time period of the sound wave. So the first 4 columns are same as the raw data table, so you just need to copy and paste it. So just select all these cells, Control C, and then paste it, Control V. Okay. Now remember that the IB requires that in every column all the values which you report should be of same number of decimal places. You can't have different number of decimal places in each cell in a particular column. Okay. So now the time taken for 10 compressions we have here. From that we need to calculate the time period, right? So this column gives you the value of the measured time period from the time which you noted down for 10 compressions. So I have given the formula also here. It is the total time for 10 compressions divided by the number of compressions. So let me explain how we get that formula. See here. So suppose I told you that 20 chocolates cost 40 rupees and I asked you one chocolate will cost how many rupees? What would you do? You want your answer in rupees, so you will do 40 rupees by 20 chocolates. So you will get 2 rupees per chocolate. So one chocolate costs 2 rupees. Just apply the similar procedure with this also. Suppose I told you that 20 compressions took how many seconds? 0.0666. 0.0666 seconds, or in terms of variables, n compressions took time taken for Tn seconds, and I want to know one compression will take how many seconds. So you want your answer to be in seconds only, so just divide the total time taken for the n number of compressions to cross Tn seconds divided by the number of compressions n. So in our example it would be 0.0666 seconds divided by 10. So later on when you do for 20 compressions, whatever time you took for 20 compressions, divide it by 20. Similarly do it for time taken for 30 compressions, divided by 30. So that would give you the time period which you measured using 10 compressions. So capital T refers to time period. Clear? So now let's get back here to the spreadsheet. So how do you type in the formula? You just type equal to, select the cell containing the time for 10 compressions. This one, click on this cell, then divide by 10. That's it. Then copy that formula, Control C, and then click on the cell below it, select all the cells in which you want the formula and do Control V. So spreadsheet is so smart, it will automatically adjust the formula. See, here it is C12 by 10, here it is C13 by 10. C13 is this cell. Here it will be C14 by 10, C15 by 10, C16 by 10. So it automatically adjusts the formula to give you the correct value for the time period. Similarly, here it would be equal to the time taken for 20 compressions divided by 20. So copy and paste it, Control C, Control V. So repeat the same for here also. Then you need to find the mean time period. So as you can see, time period is the time taken for, say, one wavelength of the sound wave to cross a given point. So it is same whether you measure it after noting the time for 10 compressions or 20 compressions or 30 compressions. So you expect the time period values to be same. If you want, you can color it differently so that it's easier. These are the total times. So let me give it a background color of, say, this color, and these are the 3 time periods. And this is the mean time period. Okay, so now how do you calculate the mean of any 3 numbers? Add the 3 numbers and divide it by 3. So equal to, select these 3 numbers and then divide by 3. Okay, you have to put the selected cells in brackets. What happened? 8 equal to, oh, you need to add them, right? I just selected, that was the mistake. So put sum, double click on that sum formula. Now select these 3 numbers, then close this bracket by clicking here, and then now divide it by 3. This is one way, or you can directly use the average formula also. Equal to, if you type AV, you will get the average function. So double click on that and select these 3 cells, then close the bracket. That is also fine. So copy this formula, Control C, and then paste it here, Control V. Okay, so this is how you measured the time period using the raw data. So okay, now theoretical time period. Theoretical time period is, see, the theoretical frequency was shown to you by the simulation. So by using the formula that time period is equal to 1 by frequency, we can calculate the frequency which we expect. So that we would call as theoretical, we would calculate the time period which we expect based on the frequencies which we used. So that is called as a theoretical time period. So it is just 1 divided by theoretical frequency. So if you are wondering how I use the relation time period is 1 by frequency, I'll explain it here. See here, okay, see, time period is the time taken for one oscillation of a particle of the medium, right? Time taken for one oscillation of the particle of the medium. It is also equal to the time taken for one wavelength of a wave to cross a point. So for longitudinal waves like sound waves, one wavelength is the distance between two consecutive compressions or rarefactions. For transverse waves, it is the distance between two consecutive crests or troughs. So in the simulation we used the fact that one wavelength is the distance between two consecutive compressions. So if this is defined as time period capital T, then frequency is number of vibrations of particle in 1 second. So it answers the question how many times each particle of the medium vibrates in 1 second. So let us say you know that 20 oscillations or vibrations took some total time of say t20 seconds. Then if you want to know one oscillation took how many seconds, we would call it as the time period, right? So let's call it capital T seconds. Then we know that time period is given by the total time divided by the n, right? In this case t20 by 20 seconds. Now if I want to know the frequency, my question would be, if the time taken is 1 second, then how many oscillations could have happened in 1 second? So for that, since I want the answer in number of oscillations, I would do total number of oscillations divided by the time taken for that many oscillations, which is t20. So my answer would be number of oscillations per second in units of number of oscillations per second. So that I would call as frequency. So now as you can compare, frequency is 20 by t20, whereas time period is t20 by 20. So they are exactly reciprocals of each other. So you can relate it as time period is 1 by frequency, which would give you 1 by 20 by t20, which is t20 by 20. So I hope now you realize how time period is actually 1 by frequency and frequency is 1 by time period. Okay, so using this we calculate the theoretical time period based on the frequencies which we used from the simulation. So here I just have to type is equal to 1 divided by the theoretical frequency. So copy and paste that formula. Now absolute error in time period would be whatever is the difference between the theoretical and the measured time period. So if so I am using the formula measured value minus theoretical value. So is equal to the measured value is here minus the theoretical value. So if this absolute error is a positive number, it tells me that whatever I measured was greater than the true value. So the error is positive. So the correction will be the negative of that. So I have to subtract that much amount from the measured value to get the true value. So that would have been the correction. So just copy and paste this, Control C, Control V. Okay. So now percentage error in my measured time period would be whatever is the absolute error divided by the total, divided by the true value of the time period into 100. So delta T is the absolute error, capital T small t suffix is the theoretical time period, which is the true value of time period, the expected value of time period, into 100. So the physical meaning of this is it tells you what fraction of the actual time period is the error. So if the error is a big fraction of the actual time period, then the percentage error would be very high. And if the error is a very small fraction of the actual time period, the percentage error would be small. So our goal should be that in every measurement we make, the percentage error should be less. It should not be more than a few percent. If it is 50%, 70%, it means something is wrong. Our data collection is wrong. So here you can see that most of the values are like maximum 7% error is only there. So that's fine. It's not too much. So the formula how to enter is equal to absolute error divided by the theoretical time period. Now put this inside brackets, then multiply it by 100, then copy and paste the formula. Okay. So now next, how to do the process data for the frequency of sound waves. So again copy the raw data table. It's the same. Control C, Control V. Then now for measured frequency, so it is just the reciprocal of whatever time period you had. So if you want, you can just do here is equal to 1 by the corresponding time period value. That will also work. So I'll show you. Is equal to 1 divided by the corresponding time period here. This. See, it works. It gives you the measured frequency. Or the actual way is, in the case of frequency, you need to know how many compressions happen in 1 second. So the total number of compressions, which is 10, divided by the time taken for 10 compressions. So the formula would be equal to 10 divided by the time taken for 10 compressions is this. So that will also give. So use any of these two formulae and paste them in the remaining cells to calculate the measured frequencies. So do this for the remaining columns also. So let's color code it. Okay. And then similarly the mean you can find as before, average of these three values, absolute error also same as before, and percentage error also same as before. Okay, fine. Next comes the task of plotting the graphs. So we want to plot a graph between the dependent and independent variable to see how they depend on each other. So we want to plot a graph between the measured time period and the theoretical frequency. So copy those two columns first. So measured time period is here, this mean one. So copy and paste it here as the dependent variable, and the independent variable should come to the left of the dependent variable column. So theoretical frequency is this column. So copy it and paste it. Control C, Control V. Similarly, copy and paste that measured time period. Control C. Remember, when you're copying cells, always do paste special, because the cell will contain formula also, and if you paste it in a different place, the formula will change itself, and that would change the values. So use paste special and click on values and then OK. So this way it won't copy the formula, it will only copy the data values. So now we will use these values to plot the graph. So select the data points, data values, and then click on insert, scatter, and select this scatter with only markers. Okay. So it automatically plots the points. Now immediately label the graph with the title. So click on chart title, above chart, and you have to write the title as dependent variable versus independent variable. So this is time period versus frequency of sound wave. Then click on axis titles, primary horizontal axis, title below axis. So that would be the independent variable, which is theoretical frequency. First variable name, comma, the symbol for that, ft, then space, forward slash, the unit, which is hertz. Now the t here should be a suffix and a subscript. So right click on it. Okay, you have to right click inside the graph. So now click on this, select only the t, keep the cursor tip on that, and then right click and do font, and then select superscript, subscript, then click on OK. So you have to do this, don't ignore this step. Now again click on layout, axis titles, primary vertical axis title, rotated title, and type the dependent variable, which is time period, comma, capital T, forward slash, space, the unit is seconds, and press enter. The title, now all the titles are done. Now you need to join these data points with a curve. So as you can see, it's not looking like they form a straight line graph, and as expected, as frequency increases, the time period is decreasing. So go to trend line, more trend line options. So by default it would select linear. You can just check each of the functions which is giving a best fit. Select display r squared value, display equation, and compare the r squared values. The best fitting function would have r squared almost equal to 1. So linear is hopeless, it's only 0.76, 0.93 for logarithmic. For polynomial you are getting 0.958. For power you are getting 0.9953. So this seems to be the best fitting so far out of all the others, right? So we'll select power and display equation and display r squared value, and you can select close. Now click on the equation, push it here, fine. So now when you do the conclusion and summary, you have to analyze this equation. What does it mean? So it's just telling you that time period is some constant divided by x power, so divided by x, because it's x power minus 1 almost, so some constant by x. Okay, so our goal is to plot a straight line graph for every experiment, because if you have a straight line graph, you can find out the slope and y-intercept, and it will have some physical meaning, and you can guess the relation between the dependent and independent variable using that. So since it is like this, you are suspecting that it is of the form y is equal to 1 by x. See here it is x power, it's minus 1.02, right? So it's like x power minus 1 is same as 1 by x. So it's like y is proportional to 1 by x. So that's why we will do that in the next graph. So 1 by x. So x is in this case theoretical frequency. So we will plot time period versus 1 by theoretical frequency, and we are hoping that we will then get a straight line graph. So again I will copy the mean measured time period as from here, and then I will calculate 1 by theoretical frequency. So I have done that here. So from theoretical frequency I have calculated 1 by theoretical frequency. So for that this formula is equal to 1 divided by this. So just copy and paste it, and you will get 1 by theoretical frequency. So I told you independent variable should be to the left, so I copy pasted it here, and then dependent variable should be to the right of that. So I copied this column and pasted it back here. So now this will be the data which I will plot. So select these data cells and then right click. After selecting it, click on the insert menu, scatter with only markers. So you will get the straight line graph. Again put the titles. So click on layout under chart tools, chart title, above chart. So this is you are plotting time period versus 1 by frequency. Now put the horizontal axis title below axis. This is 1 by frequency. The symbol is 1 by f t. Then the unit is 1 by hertz. Hertz is 1 by second, so it will actually become seconds. Now make it properly subscript. Right click, font, subscript, and the dependent variable is time period. So again go to chart tools, layout, axis titles, vertical axis title, vertical rotated title. So here you would type time period, comma, space capital T slash seconds. Now you need to draw a straight line through these points. So click on trend line, more options. So by default it is selecting linear, display equation on chart, display r squared value. You see it's a perfect 1. So that means our guess was correct. It's indeed related as time period is exactly equal to 1 by frequency. So as you can see, there is no y-intercept, it's just y is equal to mx. The c value is 8 into 10 to the power minus 6, that's practically 0. So it's, and the slope value is also 1.01, which is practically 1. So it's like a perfect straight line graph passing through origin, and the slope is 1. So it means time period is exactly equal to 1 by frequency. So this is what you have to mention when you write the conclusion. So say close. and we expect this graph to pass through the origin. So what you can do is extend this graph till it goes through origin. So for that, again go to a trend line, just remove it and draw the trend line fresh. Select display equation, display r squared value, and in backward, see here it's almost 0.001. So that many units you want this line to go back along x-axis. So on x-axis, see the value of this first data point, it's almost 0.001. So that many units you type here so that it will go back. So little more gap is left, so add little more, say 0.0005 units more. Now it's crossing, so reduce it a bit, yeah, or reduce it even a little more, yeah. Now it's fine, it's exact, so you can see it's exactly passing through the origin. That's what you need to show. Okay, next I'll also show you how to put the error bars. Where are the error? Here we are having absolute error in measured frequency, right? Okay, we plotted a graph between time period, so absolute error in time period, but it's almost negligible since this experiment done theoretically using simulation. The errors are negligible, there is no point in plotting it. In another experiment, when we do it using the actual setup, you will find that the errors are very significant. That time I will show you how to plot the error bars. So for this experiment, it's enough if you just plot the graph like this. So now what will you write in the conclusion and evaluation? In the conclusion, I want you to mention that the graph was plotted between time period and frequency, and the spreadsheet gave me the equation y is equal to 1.1 into x power minus 1, which is y is equal to 1 by x. So it made me think that the time period should be related as 1 by theoretical frequency. So to verify it and to plot a linear graph, I plotted time period versus 1 by frequency, and as expected it gave me a straight line graph, and the equation was y is equal to 1x. So from that I get that time period is actually equal to 1 by frequency. That's the conclusion. And the evaluation would be, since the experiment was done on a simulation, the theory is exactly verified, but if we do it in a real lab setup, there would be a lot of error in the measurements, and we would find that the r square value would not be a perfect one when we plot the graph. I think that should be enough.